The conveyor belt never stops. 24 hours a day, 7 days a week, it carries the remnants of human ambition through the sterile corridors of the Nike recycling facility in Ruse Shoe, located on the outskirts of a European industrial park, where the air smells faintly of synthetic rubber and ozone from high-voltage sorting equipment. The shoes arrive in enormous wireframe gaylords, each container holding nearly a ton of discarded athletic footwear. They come from donation bins positioned outside sporting goods retailers, from marathon finish lines, from university athletic departments purging their equipment rooms. They are Air Maxes with blown-out heel counters, soccer cleats with separated outsoles, basketball shoes whose midsole foam has compressed into useless density after thousands of impacts against hardwood. Each pair tells a story of kinetic energy absorbed and released, of chemical bonds stressed beyond their elastic limit, of materials that have fulfilled their designed purpose and now face obsolescence. But obsolescence in this facility is merely a transition state. The first stage of processing begins with manual sorting at stainless steel tables beneath banks of LED lighting calibrated to 6,000 Kelvin, approximating the spectrum of midday sunlight. Workers wearing nitrile gloves examine each shoe, their hands moving with practiced efficiency born from processing tens of thousands of units. They remove metal eyelets, pull out laces, extract insoles that will be processed separately. Any shoe containing more than 10% non-Nike materials is diverted to a secondary stream. Quality control is absolute. The sorting process is not merely organizational, but taxonomical, categorizing footwear by construction method, material composition, and vintage. A shoe manufactured in 1995 using older polyurethane formulations will follow a different processing pathway than a 2023 model built with supercritical EVA foam and thermoplastic polyurethane caging systems. The workers know this intuitively, their pattern recognition honed by repetition, their fingers reading the subtle textures that betray a shoe's chemical genealogy. From the sorting tables, the shoes advance to the first mechanized stage, the rough shredder, a horizontal shaft machine with dual rotors that counter-rotate at differential speeds. The geometry is precise, hardened steel teeth, each shaped like an industrial can opener blade, that intermesh with calculated clearances measured in millimeters. As shoes enter the shredding chamber, the rotors seize them with violent efficiency. The sound is apocalyptic, a grinding roar punctuated by sharp cracks as thermoplastic shanks fracture and carbon fiber plates shatter. The shredder does not simply tear the shoes apart. It subjects them to shear forces exceeding 20,000 pounds per square inch, forces sufficient to overcome the molecular bonds in vulcanized rubber and rip through the laminated layers of modern performance footwear. What emerges from the discharged chute is barely recognizable as footwear. The shoes have become a heterogeneous stream of fragments, a chaos of materials ranging from thumbnail-sized rubber chunks to long strips of engineered mesh, from granulated midsole foam to twisted remnants of heel counters still retaining their original curvature. This fragmented material flows by gravity feed into a pneumatic conveying system, where high-velocity airstreams carry the debris through enclosed ductwork to the next processing stage. The air speed is calibrated precisely, adjusted in real time by pressure sensors and flow meters that communicate with programmable logic controllers. Different materials have different aerodynamic properties. A piece of lightweight fly-knit fabric will be carried at lower air velocities than a dense rubber outsole fragment. The system exploits these differences, creating the first crude separation. Lighter materials are deposited in one cyclone separator, while heavier materials continue through the duct to a secondary collection point. This is pneumatic classification, an elegant application of fluid dynamics to materials recovery. And it happens continuously at a throughput rate of approximately 4,000 pounds per hour. The material now enters the domain of the granulator, a machine that represents the pinnacle of size reduction engineering. Unlike the aggressive brutality of the rough shredder, the granulator operates with calculated precision. Its rotor spins at 600 revolutions per minute, driving an array of cutting blades past a fixed bed knife with clearances held to within 50 micrometers. The cutting action is shearing rather than impact-based, producing particles with consistent size distribution. The granulator chamber is cooled with chilled water circulating through a jacketed housing, maintaining operating temperatures below 40 degrees Celsius to prevent thermal degradation of thermoplastic materials. As rubber particles are sheared to progressively smaller sizes, they begin to exhibit the properties of granular materials rather than solid objects. A transformation occurs at the threshold where individual particles measure less than 5 millimeters in diameter. At this scale, the rubber fragments begin to flow like a dense fluid, avalanching down the discharge chute in continuous streams that shimmer under the facility's lighting, each granule catching and reflecting light from its freshly cut surfaces. The granulated material now faces its most crucial test: separation by material type. This is where industrial processing transcends mere mechanical destruction and enters the realm of material science. The separation system begins with a density classification tank, a water-filled vessel where carefully controlled turbulence keeps particles in suspension. Rubber, with its density of approximately 1.2 grams per cubic centimeter, behaves differently in this aqueous environment than ethylene vinyl acetate foam, which has a density closer to 0.2 grams per cubic centimeter. The EVA foam floats, forming a raft at the water surface that is skimmed off by rotating paddles and conveyed to dedicated processing lines. The rubber sinks, accumulating at the tank's conical bottom where a screw conveyor extracts it for further processing. But density separation alone is insufficient for the complex material matrix of modern athletic footwear. The separated streams now encounter optical sorting technology that operates at speeds incomprehensible to human perception. High-resolution cameras mounted above a vibrating conveyor capture images at 2,000 frames per second, examining each particle as it passes beneath the lens array. The cameras do not simply record visible light. They are hyperspectral sensors capable of detecting electromagnetic radiation across wavelengths from ultraviolet through near infrared. Different polymers have unique spectral signatures. Thermoplastic polyurethane absorbs and reflects light differently than styrene butadiene rubber, which differs from natural rubber, which differs from polyester mesh. Machine learning algorithms trained on millions of spectral profiles make identification decisions in microseconds. When a particle is identified as belonging to a specific material category, compressed air jets positioned on 12-millimeter centers along the conveyor width fire with millisecond precision, ejecting the targeted particle into designated collection bins. The air pressure is 90 pounds per square inch, the valve response time is 2 milliseconds, and the sorting accuracy exceeds 95%. It is a ballet of pneumatics and photonics playing out thousands of times per minute in a cascade of decision-making that would paralyze human operators. The sorted rubber stream proceeds to cryogenic grinding, a process that exploits the glass transition temperature of elastomeric materials. Liquid nitrogen at minus 196 degrees Celsius is injected into the grinding chamber, flash freezing the rubber particles until they become brittle and glass-like. In this frozen state, the material can be pulverized to extremely fine particle sizes impossible to achieve at ambient temperature. The cryogenic mill's rotor, spinning at 3,600 RPM, impacts the frozen rubber with kinetic energy sufficient to fracture it into particles measuring 200 micrometers in diameter, fine enough to pass through a 70-mesh screen. The process is energy-intensive, but essential for creating rubber powder of sufficient fineness for reincorporation into new manufacturing processes. The ground rubber exits the cryogenic chamber through a heat exchanger, where it gradually returns to ambient temperature in a controlled manner that prevents moisture condensation on the particle surfaces. What emerges is a dry, free-flowing powder that bears no visual resemblance to the shoes that entered the facility hours earlier. The foam materials follow a different pathway, one dictated by the thermoplastic nature of EVA and polyurethane. These materials are fed into a compounding extruder, a machine that melts, mixes, and reshapes polymer chains through the application of heat and mechanical shear. The extruder barrel contains multiple heating zones, each precisely controlled to maintain optimal processing temperatures. For EVA foam recycling, the barrel temperature profile ranges from 160 degrees Celsius at the feed zone to 180 degrees Celsius at the die. Inside the barrel, a rotating screw with a carefully designed flight geometry conveys the material forward while simultaneously generating shear heat through friction. The polymer melts, its long molecular chains sliding past each other in a viscous flow regime characterized by non-Newtonian behavior. As color pigments from the original shoes, vibrant reds, electric blues, neon greens, blend into a mottled stream that swirls hypnotically as it flows through the transparent observation ports along the barrel. At the die end, the molten polymer is forced through a perforated plate and into a water bath, where it solidifies into spaghetti-like strands. These strands are pulled through a pelletizer, a rotary cutting system that chops them into uniform cylindrical pellets approximately 3 millimeters in length. The pellets tumble into collection boxes, clicking against each other with a sound like distant rain on a tin roof. The textile materials, having been separated by the optical sorting system, face yet another processing challenge. Athletic shoe textiles are engineered fabrics, often combining polyester fibers with thermoplastic polyurethane films, elastane for stretch, and surface treatments for water resistance. This material complexity makes them unsuitable for simple mechanical recycling. Instead, they are directed to a chemical recycling pilot line where depolymerization reactions break down the polymer chains into their constituent monomers. The process begins with solvent treatment in a pressurized reactor vessel. Polyester fabrics are submerged in ethylene glycol heated to 200 degrees Celsius under pressure that prevents the solvent from boiling. Under these conditions, the ester bonds linking the polymer chains begin to hydrolyze, breaking apart in reverse of the original polymerization reaction that created them. The process takes several hours and monitored continuously by inline spectroscopy that tracks the conversion rate. When depolymerization is complete, the reactor contents are cooled and filtered. The recovered monomers, purified terephthalic acid and ethylene glycol, emerge as crystalline solids and clear liquids that are indistinguishable from virgin petrochemical feedstocks. The polymer chains have been unwound, their history erased at the molecular level. Meanwhile, in a separate wing of the facility, the rubber powder and foam pellets are being characterized with laboratory precision that would satisfy pharmaceutical manufacturers. Technicians in white cleanroom garments operate analytical instruments arrayed along benches lit by the cool glow of LCD displays. A thermogravimetric analyzer heats minute samples of the rubber powder under controlled atmospheres, measuring weight loss as a function of temperature to determine the material's thermal stability and volatile content. A differential scanning calorimeter reveals the glass transition temperature and melting behavior of the foam pellets, data essential for optimizing their reprocessing conditions. An infrared spectrometer bombards samples with infrared light, producing absorption spectra that serve as molecular fingerprints, confirming the chemical identities of each material stream and detecting any contamination that might compromise downstream use. The data flows into a materials database, creating a digital twin of the physical inventory, ensuring that when this recycled material is sold to manufacturers, its properties are known with greater certainty than many virgin materials. Holstad, the rubber powder, finds its destiny in sports surfacing applications. In a manufacturing facility 200 kilometers distant, it is combined with polyurethane binders and poured onto running tracks and basketball courts, where it will absorb the impacts of athletes for the next decade. The material comes full circle. From shoes that cushioned running strides to surfaces that perform the same function, its molecular structure is still capable of elastic deformation and energy return despite its journey through shredders and grinders. The foam pellets are compounded with virgin EVA in carefully controlled ratios, then injection molded into new midsoles that carry performance specifications indistinguishable from those made from entirely new materials. Chemical testing confirms that the recycled foam retains 94% of its original mechanical properties. In blind testing, professional athletes cannot distinguish shoes made with 20% recycled foam content from all virgin alternatives. The fabric monomers are repolymerized in chemical plants, reforming into polyester polymers that are spun into fibers and woven into new textiles. The molecular cycle completes itself. Carbon and hydrogen atoms that once formed the upper of a running shoe now forming the upper of its descendant, atoms that are effectively immortal, cycling through forms dictated by human engineering. But not all materials achieve such elegant resurrection. A small fraction of the input stream, approximately 8% by weight, emerges as residual waste that cannot be economically processed with current technology. These are the complex composites, the materials where adhesives have created inseparable bonds between dissimilar polymers, the small metal components too dispersed to recover, the contaminated materials that failed quality checks. This fraction is diverted to energy recovery, incinerated in waste-to-energy plants, where its hydrocarbon content is converted to electricity that powers the regional grid. It is a pragmatic acknowledgement that even advanced recycling systems operate below perfect efficiency, that thermodynamics and economics impose limits on materials recovery. The facility does not celebrate this fraction, but neither does it apologize for it. In a world where the alternative is landfilling 100% of discarded shoes, recovering 92% represents a revolution. The facility operates with machine efficiency, but is ultimately a human creation, sustained by human decisions. Every shoe that enters represents a choice, the choice to return it rather than discard it in household waste. The donation bins scattered across cities are nodes in a reverse logistics network as complex as the original distribution system that brought the shoes to retail. Collection trucks follow optimized routes, gathering material from bins, consolidating it at regional hubs, then shipping it in full containers to processing centers. The economics are marginal. The value of the recovered materials barely exceeds the cost of collection and processing. The operation is sustained by brand value, by Nike's calculation that environmental leadership provides competitive advantage in markets where consumers increasingly demand corporate responsibility. It is industrial ecology implemented not from altruism, but from strategic necessity, a recognition that the social license to operate in the 21st century requires demonstrable action on waste and carbon emissions. The environmental mathematics of the operation are complex and contested. Life cycle assessments conducted by independent consultants suggest that recycled rubber used in sports surfaces reduces carbon emissions by approximately 60% compared to virgin rubber from petrochemical sources, primarily because it avoids the energy-intensive polymerization reactions required to create new synthetic rubber. And the recycled foam provides more modest benefits, approximately 25% emissions reduction, because the reprocessing energy requirements partially offset the avoided virgin production. The fabric recycling, being chemically intensive, shows the smallest benefit, approximately 15% emissions reduction. Critics point out that these figures depend heavily on assumptions about energy sources, transportation distances, and substitution ratios. Proponents counter that even modest emissions reductions, multiplied across millions of shoes annually, represent meaningful climate action. The debate plays out in peer-reviewed journals and sustainability reports, each side marshaling data, while the machines continue their work with mechanical indifference to the arguments of humans. Inside the facility's control room, operators monitor the process through a supervisory control and data acquisition system displayed across 6 large monitors. Each screen shows a different aspect of the operation: real-time throughput rates, material quality metrics, equipment status indicators, energy consumption trends, inventory levels, shipping schedules. The interface is dense with information, numbers, and graphs, updating multiple times per second, the digital heartbeat of industrial metabolism. Alarms are configured to alert operators when parameters drift outside acceptable ranges. When the optical sorter's sorting accuracy drops below 93%, an alarm sounds, and the system automatically reduces the conveyor speed, giving the air jets more time to react, trading throughput for quality. When the granulator's power consumption spikes, suggesting dull cutting blades, a maintenance alert is generated and scheduled into the next planned downtime window. The system is self-monitoring, self-adjusting, executing decisions programmed by engineers who designed resilience into the process logic. As evening falls, the facility lights remain at full intensity. There is no night shift change because there is no distinction between day and night in the operational cycle. The conveyors run, the shredders roar, the optical sorters fire their pneumatic jets, the extruders maintain their temperature profiles. A truck backs up to the loading dock, its diesel engine rumbling as it positions to receive super sacks filled with rubber powder destined for a sports surfacing manufacturer in Belgium. Another truck departs, all carrying gaylords of foam pellets to an injection molding facility in Germany. The facility is a node in a material flow network that spans continents, a network that is invisible to the consumers who dropped their worn-out shoes into donation bins and never considered what might happen next. The transformation that occurs within these walls is not magic, but applied material science, the systematic exploitation of physical and chemical principles to manipulate matter at scales from meters to micrometers. Yet there is something almost miraculous in watching the progression from coherent footwear to molecular chaos to reorganized utility. The shoes die, but their materials persist, finding new forms that serve analogous functions. It is industrial reincarnation. They are driven not by spiritual beliefs, but by thermodynamic laws and economic incentives. The carbon atoms that form the backbone of these polymers are ancient, forged in stellar nucleosynthesis billions of years before Earth existed, cycled through countless forms over geologic time, temporarily locked in petroleum deposits until human industry extracted them and transformed them into consumer products. Now they cycle again on human time scales, moving from shoe to granule to surface to waste to shoe in loops measured in years rather than epochs. Standing on the catwalk above the main processing floor, the sound is overwhelming, an industrial symphony of mechanical violence and precision engineering. The shredders growl, the granulators whine, the pneumatic hiss of the optical sorter, the hydraulic sigh of the compounding extruder, of the ventilation system's continuous roar. This is the sound of transformation, of entropy being locally reversed through energy input, of human ingenuity applied to the problem of its own excess. The facility processes approximately 12 million shoes annually, preventing roughly 20,000 tons of material from entering landfills. It is a significant achievement, yet it represents less than 5% of the athletic shoes discarded each year. The implication is sobering. Even this sophisticated operation, this cathedral of recycling technology, barely scratches the surface of the waste stream it addresses. Scaling to process all discarded athletic footwear globally would require dozens of such facilities, billions in capital investment, fundamental changes to product design to enhance recyclability, and behavioral shifts to ensure collection rates approach 100%. The future of the operation depends on technological evolution and market dynamics that remain uncertain. Research teams are developing new shoe designs where components can be easily separated without mechanical shredding, where adhesives are replaced with mechanical fasteners or reversible bonds that break under specific conditions. Material scientists are formulating new polymers designed from inception for recyclability, with molecular structures optimized for depolymerization and repolymerization. Business strategists are exploring service models where consumers lease shoes rather than purchase them, ensuring return at end of life becomes contractual rather than voluntary. These innovations exist in pilot programs and research papers, are not yet ready for the mass market, but pointing toward a future where recycling is designed into products from the beginning rather than retrofitted as an afterthought. Whether that future materializes depends on regulatory pressures, consumer preferences, and the economics of virgin versus recycled materials, variables influenced by oil prices, climate policy, and cultural attitudes toward consumption and waste. The final product of this facility, the rubber powder, the foam pellets, the recovered monomers, carries a paradoxical quality. It is both waste and resource, refuse and feedstock, the end and the beginning. When it leaves the facility, it enters supply chains where its recycled origin becomes invisible, subsumed into products that make no visible distinction between virgin and recovered materials. A basketball court surfaced with recycled rubber performs identically to one surfaced with virgin rubber. A shoe midsole containing recycled foam flexes and rebounds with the same mechanical characteristics as its all-virgin counterpart. The materials have been purified, standardized, brought into conformance with specifications that make their history irrelevant to their function. This is the ultimate success of the recycling operation, the moment when recycled content becomes truly equivalent to virgin content, when the loop closes not just materially, but functionally and economically. Yet the visibility matters for reasons beyond function. When Nike markets shoes made with recycled materials, when athletic facilities advertise their sustainable surfaces, when environmental reports quantify the tons of waste diverted from landfills, the recycling operation achieves a second purpose beyond materials recovery. It becomes narrative, becoming proof that industry can change, that consumption need not be linear, that waste is a design flaw rather than an inevitability. Whether this narrative is genuine commitment or sophisticated greenwashing is debated with the intensity that characterizes all corporate environmental claims. The skeptics see brand management masquerading as environmentalism, pointing out that the recycling program, however sophisticated, does not address the fundamental issue of overproduction and overconsumption. The defenders see pragmatic progress, incremental improvement within existing economic systems, real tons of material diverted from real landfills. Both perspectives contain truth. The facility is both genuine materials recovery and strategic corporate messaging, both environmental action and brand equity building, both solution and distraction from larger questions about consumption patterns in wealthy societies. The machines, indifferent to these debates, continue their programmed tasks. Another gaylord of shoes tips into the sorting area. Another batch of rubber granules flows into the cryogenic mill. Another load of pellets is loaded onto a departing truck. The process is continuous, relentless, mechanical. In a world generating waste at accelerating rates, this facility represents a counterforce, a reverse engine that takes disorder and extracts temporary order, that sees value where others see refuse, that treats discarded products not as endings, but as beginnings. It is imperfect, incomplete, insufficient to the scale of the challenge, yet it exists, functions, persists. In the grand accounting of industrial civilization's material flows, it is a small correction, a minor reversal in streams of matter that otherwise flow in one direction toward dissipation and dilution. But small corrections, replicated and scaled, can redirect rivers. Whether society possesses the will to build enough of these facilities, to redesign enough products, to transform enough consumption patterns remains the central question. The technology exists. The engineering is proven. What remains uncertain is whether humanity will deploy these solutions at the scale and speed that the accumulating waste crisis demands.